Hi, Assalamualaikum. So today we would like to present about our group project for Mathematics Engineering Technology 2 about Newton's law of cooling using Euler and Runge-Kutta method. Assalamualaikum and hi, my name is Imanina. I will start with the introduction. Many real-life problems like heat transfer or population growth are modeled using different equations, but they are often too complex to solve with algebra. Numerical methods provide step-by-step solutions that help us estimate and understand how systems behave over time. There are several types of numerical methods for solving ODE. The Euler method is simpler but less accurate, while the Runge-Kutta method gives better precision. Both are useful to predict a system behavior without needing a direct formula. In this project, we apply both methods to get the solution. Our scenario involves a metal rod initially at 150 degrees Celsius, cooling down in a 30 degrees Celsius room. The process is modeled using Newton's law of cooling, written as dt over dt equals minus k times t minus ta. In our case, k is 0.1 per minute and the step size is 1 minute for a total of 5 minutes. Both Euler and Runge-Kutta method are used to solve this problem. First, we use Euler method with the formula Tn plus 1 equals Tn plus h times f of Tn. The function ft equals negative k times t minus ta, or in this case, negative 0.1 times t minus 30. Using this, we calculate the temperature at each minute. As shown in the table, we started with 150 degrees Celsius and ended at 100.86 degrees Celsius after 5 minutes. Here is the output of our C++ program using Euler's method. The result matched our manual calculation exactly, which confirmed that the formula was correctly applied in the code. At the 5-minute marks, the temperature is 100.86 degrees Celsius. This consistency shows that the method is reliable and minimizes human error.
Okay, I'm your Izzati Khadijah. Now, let's move to the second method we use, which is the Runge-Kutta fourth order method, often known as RK4. Compared to the Euler's method, Runge-Kutta gives a much more accurate estimation because it calculates 4 different slope values at each time step. These slope values are known as K1, K2, K3, and K4. The formula looks a bit complex, but it works like this. We start with the initial temperature and calculate K1, which is the slope at the beginning of the interval. Then, we use K1 to estimate the midpoint and calculate K2. So, we repeat this to get K3 and finally calculate K4, which is the slope at the end of the interval. Then, we combine all these values using a weight average to find the next temperature value. This is repeated for each time step. Using this method manually, we estimated the temperature at each minute for 5 minutes. The temperature dropped from 150 degrees Celsius to 102.78 degrees Celsius after 5 minutes. The result is smoother and more realistic compared to Euler's output. Okay, after completing the manual calculation, we also implemented the same logic using C++ programming. The output from the code was identical to our manual results, confirming that the Runge-Kutta formula was correctly applied in the program. So at 5-minute mark, the final temperature was also 102.78 degrees Celsius. So this consistency between manual and programmatic solutions prove the strength of numerical methods when supported by computational tools. It also shows that programming helps eliminate manual errors, especially in long or repetitive calculations. So for the result and discussion, let's compare the results of both numerical methods. So using Euler's method, the final temperature after 5 minutes was 100.86 degrees Celsius. For Runge-Kutta, it was 102.78 degrees Celsius. While the difference might seem small, it reflects the accuracy level of each method. Euler method is simple and fast, but can accumulate errors over time. So this is because it only considers the initial slope in each step, which doesn't reflect how the system might behave midway or near the end of the interval. On the other hand, the Runge-Kutta method calculates several slope estimates at different points within each step and then averages them. This leads to a more reliable and accurate output. In both methods, our manual calculation method exactly with our C++ outputs. This consistency shows that our formulas and programming logic were correctly applied. It also demonstrates how helpful programming can be when applying mathematical techniques to engineering problems. So, in conclusion, this project helped us understand how numerical methods play an important role in solving real-world engineering problems that involve differential equations. The Euler method is useful for quick approximations, but it's less accurate over time due to its basic linear approach. Meanwhile, the Runge-Kutta method, though more complex, it offers a higher level of accuracy, which is often necessary in engineering applications. Through this project, we also saw how programming C++ can support manual calculation by automating steps and minimizing error. This experience not only strengthened our mathematical and coding skills, but it also improved our collaboration, communication, and problem-solving abilities as a team. We hope this project presentations gives a clear picture of how theory, computation, and teamwork come together in solving engineering problems efficiently. So that's all from us. Thank you.